Hello and welcome to this case study of an XC90 petrol vehicle with a misfire. And it's a case study with no real conclusion but concise diagnosis. So it's all about how we use Pico to diagnose these problem vehicles and be able to present accurate results to our customer so they can make an informed decision, because diagnosis ends once dismantling begins. So we need to know exactly what we're looking for based on our test results, based on knowledge and experience. A training, of course, it all forms part of this delivery that we can hand over to the customer. So let's make a start then. This XC90 misfire, clear misfire. It'd be quite easy to determine what cylinder the misfire is on as we go through. How do we tackle such symptoms of misfire? Well, of course, experience, probability, and accessibility. Those pretty much govern how we approach these challenges. Non-intrusive is the key word here, non-intrusive engine evaluation. We want to remove as fewer components as possible. There's always that risk, isn't there, when you start removing things, refitting, disconnecting. You can actually rectify the fault and not actually know what was the original cause and what you've actually done to cure the issue. So we'll keep everything non-intrusive as possible. So first of all, relative compression. That's really the first move. With this, we knew that we had a misfire on cylinder 5. So let's dig and delve a little bit deeper. So we have to check the condition of the 12-volt battery. We want to spin this engine to carry out a relative compression test. And you'll see here in these test results, on this occasion, the battery failed. So before we even start, we've got a repair bill of at least £100+ to replace the battery. Now, that may or may not influence the customer's decision. And as we go on, we'll see why. Think about, let's say, if it's a spark plug that's the cause of the misfire. That's fairly straightforward, and I think a customer would probably go for that and a new battery. But however, when it comes to an engine that requires dismantling, all the labour that's involved there, plus another £100, etc. for a battery, it all starts to pile up. And it's the fact that we can hand all this information back to the customer without any nasty surprises at the end of a repair or during the repair process. So in the data here, we can see that our battery has failed on capacity. The capacity entered was 750 cold cranking amps, and we achieved 40% of that. So in this scenario, we're going to have to support this battery to continue with a relative compression test. And here we are. This is possibly the most straightforward test that we have in the Pico Diagnostics suite. Probably PicoScope as well, for that matter. It's no more than connecting a test lead across the battery connected to channel A, disconnect or prevent the engine from starting, crank the engine with a foot on the gas pedal, so gas pedal is right down, throttle is wide open, and these results speak for themselves. Let's just have a look there. We've got a cylinder down. Clearly, it looks like we have no compression at all on one cylinder. Remember, it's a relative compression test, so we're comparing the worst performing cylinder with the best performing cylinder. Now, we found a cylinder that's down, but how do we know it's cylinder 5? It's at this point that we have to switch to PicoScope, and that's what we do here. So for this test, we incorporate a synchronization signal. So what is that? Well, you'll see here on channel A, we've got battery voltage. On channel B, we've got battery current. And on channel C, we've got the ignition event, what we call the PCM trigger signal, to the ignition coil pack cylinder 1. Now, we can also use the coil on plug probe as well. It's whichever is easier. I certainly like using the PCM trigger signal because we have a hands-free signal there. We don't have to hold the coil on plug probe or tape it in position. We've got a good connection. Right, based on the firing order, which on this was a 6-cylinder, it's 153624, we're going to have a look at, well, see if we can confirm if cylinder 5 is our offender. So let's have a closer look. So here on the left is the zoomed out or the full image. And on the right hand side, we have zoomed in and we have hidden channel A. So what we've got now is channel B against channel C. Now look at the alignment on channel C. Channel C aligns with a peak that we know is a compression peak. It's a high current ramp from cylinder 1. Following the firing order, look what happens to current flow into the starter motor then as we go on to the next cylinder, cylinder 5, completely low. We then get a recovery back onto 3, so we know 3 is okay. Looking at 6, 6 is lower, but still much higher than 5. 2 and 4 pretty much the same. 1 looks like it's slightly lower, but certainly as we drop down onto the next cylinder, our current drops down slightly. Sorry, our current drops down considerably. Cylinder 5 is definitely our offender. What this is telling us is that the effort on the starter motor is minimal to compress cylinder 5 for whatever reason that may be. That's represented here by low current flow during cylinder 5 compression stroke. So let's move on. We'll stay with the non-intrusive engine evaluation theme, keeping everything as non-intrusive as possible. Here we're going to look at exhaust gas pulsations. So this is a real neat test where we place either the pressure transducer or a first look sensor, whatever it may be, into the exhaust tailpipe. Remember to secure it because we don't want any pulsations that we can attribute to movement. With this one, we actually crank the engine, but with no combustion, because the best way to look at exhaust gas pulsations is during cranking without combustion. We just want to have a look at pulsations that we can attribute to the compression, to the pumping action of the engine. In addition, we're going to add something else called the Microsoft Pressure Waveform Overlay Chart. What an overlay chart does, it enables us to determine what events are taking place in the 4-stroke cycle on every cylinder at any given point in time within our graph. So let's have a look. Once again, on the left, we've got the zoomed out, and on the right, we are zoomed in. So we've kept our synchronization signal. This is channel B, and this is the red waveform. And we know that that is the firing event for cylinder 1. Moving up the chart, the next event or the next firing event in the firing order is cylinder 5. And that's what we want to focus on here. So I've added 2 magenta vertical lines, which are part of the pressure waveform overlay software. And we can see there that we have the exhaust stroke for cylinder 5 between the 2 magenta dotted lines. Focus on the pulsations that we can see in the exhaust, and I've actually highlighted the area of interest with a blue circle. So we can see there that we have an additional pull. This is a push or a pull back into the exhaust when cylinder 5 is on its exhaust stroke. They call this the dollar bill test. This is where you traditionally place a dollar bill against the tailpipe of a vehicle. And when there was a misfire, momentarily it would pull the dollar bill back towards and seal the tailpipe. So why is that happening? Why is there a suction in the exhaust during the exhaust stroke of cylinder 5? Well, let's think this through. When the exhaust valve opens on cylinder 5 and there is no combustion, we have a lower pressure. We'll possibly, and in this scenario, have a negative pressure above the piston. So once the exhaust valve opens, that negative pressure is presented to the exhaust system, and atmospheric pressure at the tailpipe will be pulled back to meet or to compensate for the negative pressure as a result of what lies above the piston when the exhaust valve opens. We can clearly see that there, where we have that deeper pull during the exhaust event of cylinder 5. Okay, so let's move on. We're gathering evidence as we go. We know we've got cylinder 5 compression down. We know that when cylinder 5 opens its exhaust valve, that there is a negative pressure above the piston. So what else can we add? Well, let's keep going with non-intrusive and using the pressure transducer. And in this scenario, we've used a pressure transducer in the intake manifold. So on this occasion now we have combustion because we want to pull a negative pressure inside the manifold. Best way to do that is to have the engine running at idle speed. So our engine is running with our misfire, of course. Everything is still connected, but we are tapped into the intake manifold with a pressure transducer. And because we can, we'll also leave the first look sensor in the exhaust system. Again, we'll add the pressure overlay waveform chart so we can determine what's going on at any given time. Let's focus on channel D here. Look what happens during every intake pull. So this is every suction event inside the intake manifold when the inlet valve opens for each cylinder. So staying with the overlay chart, let's focus on cylinder 5, and our intake is denoted with the colour yellow. Cylinder 5 I've identified with the 2 arrows that point downward, and during the intake stroke of cylinder 5 we can see we have less of a pull on the intake manifold. Less negative pressure appears inside the intake manifold during the intake stroke of cylinder 5. Again, I've highlighted that with this blue circle. Also take a look at channel A, which is the exhaust gas pulsations, and how they have changed by comparison to what we saw previously, because now we have combustion. Not only do we have combustion, we have the complexities of a misfire inside the exhaust system that generates all kinds of buffeting, all kinds of dynamics that it's really difficult to determine what is happening at any given time. But with that said, focus on cylinder 5 exhaust event in the overlay chart, which is denoted with a brown colour. And the circle that I've highlighted there, that how we've had disruption in the exhaust gas pulsations during the exhaust event of cylinder 5. So we can see that we do have formation round ignition points of cylinder 1. The pulsations, whilst they're not even, they certainly are regular. And then at the point of exhaust on cylinder 5, we have this deformation, then the recovery, and then we almost return back to some sort of pulsations again. But the message here is that during our misfire event, cylinder 5 opens its exhaust valve and presents uneven dynamics to exhaust gas pulsations. Finally, again, returning to channel D, notice the sinusoidal pattern that we have. Although there is a sawtooth there, and the sawtooth is generated from each intake pull, the overall sinusoidal pattern is as a result of instability of the engine with the misfire. Because think about the misfire, there will be a point during the 4-stroke cycle where our engine speed will be reduced. So we're going to have this event, or this sort of change in engine speed, which will ultimately affect the overall sawtooth pattern that we're seeing here. So a couple of things to contend with. One is the intake pull. 2 is the sinusoidal overall pattern as a result of misfire. Had this been a perfectly running engine, we would still have the sawtooth, but rather than this sinusoidal effect, we'd have a straight line. Okay, so now it's time to become intrusive. And really, when you think about it, this is the most intrusive test so far. Up to now, it was relative compression, it was a battery test, it was a pressure transducer into the exhaust, and again in the intake, so no more than perhaps fetching an engine cover off and maybe disturbing a hose. But now we'll actually measure cylinder pressure. And for this, we use the pressure transducer. We'll compare cylinder 2 in blue against cylinder 5 in the magenta, the pink colour. There's a couple of things to note here. I will just read them from here, but we'll also then go on to the next screen where we can analyse much further. It's very easy to see that cylinder 5 compression, the pink, the magenta waveform, is too low. It's low by comparison. We also have a deeper expansion pocket on cylinder 5, which I'll come to. We also have to consider the swept volume. Let us go on to the next waveform so I can actually analyse this with much more detail. So starting with in-cylinder analysis, let's have a look at the waveform within PicoScope 7. It's clear to see, isn't it, straight away that cylinder 2, the blue waveform, is much higher for peak compression than cylinder 5, the pink waveform. What we are interested in initially is peak pressures, that they are even. So across every peak pressure event, we want to see that the peaks all align. Any sort of deviation from peak pressure suggests that we may have poorly seated valves. Don't be too alarmed by the fact that compression is down at 5 bar for the good cylinder. Remember, this vehicle is idling, so we are at about 800 RPM, but the throttle is closed, which means the engine is starved of air. So if we can't pull air in, we can't compress, hence we have low compression. Moving along to symmetry, the compression towers, look at the magenta one here. Notice how the rising pressure in terms of the distance between the peak, the rising pressure and the zero phase ruler on the rising section compared to the falling section is much wider. The distance between here up to 0 and then from 0 to, let's say, around about, I'd say probably about 40 degrees, something like that, is different. That gives us a leaning compression tower. A leaning compression tower is an indication of cylinder leakage. Next then, let's look at the expansion pocket. We can see how we are deeper in our expansion pocket below the 0 line here, which is atmospheric pressure, compared to the good cylinder. And yes, the good cylinder is starting from a higher point. So to be fair, we've got to lose or decay all of that positive pressure before we fall into a negative pressure. Nevertheless, the fact that we can go into a deeper expansion pocket with less pressure, less peak pressure, suggests that our swept volumes are equal. So whilst that's not categorically true, at least there is an indication that the fact the cylinder performs in such a way that with a low pressure, it can still generate a deep expansion pocket. Had our swept volumes been different, it may be that we'd have a low compression and a lower expansion pocket. Okay, moving along, we're looking at the exhaust valve open event, which occurs around about 150 degrees, give or take. On this vehicle, we have VVT disconnected, which is always good practice when we're trying to analyse waveforms between cylinders. We don't want any VVT intrusion. Focus on this area here on the blue waveform, how we have a clear defined rise moving up to our atmospheric pressure, the point where our exhaust valve opens. Look though at the magenta, how this is more dished in formation, so less pronounced, and also much later, suggesting we're having a partially or maybe slightly retarded exhaust valve open event, and not clearly defined either. Moving on to 360 degrees, look how late the magenta waveform exhaust valve closes, or the point where we achieve maximum negative, initially maximum negative intake pressure. So the difference between these two is 22 degrees of crankshaft rotation. So there is clearly a delayed or retarded exhaust valve fully closed event, an inlet valve fully open event. Now, how does that affect pressure? Well, let's move along now to the area here where we are looking at where we start to compress. This will be the inlet valve close event, and by comparison, they are different. So if on one cylinder, we are closing the inlet valve later, retarded, it means we've got less of an effective compression stroke, so less degrees of crankshaft rotation in which to compress that cylinder. So hopefully that you can see here that starting from left to right with the waveform, there are key points in the waveform to note. And I'll just recap on those. They are, first of all, peak pressures, compression tower symmetry, the expansion pocket, the exhaust valve open event, and the known exhaust valve close event, where we achieve the initial maximum negative intake pressure. Moving along then, the inlet valve close event, and once again, the compression event and the compression tower symmetry and the effective compression stroke. So in other words, depending on where we close the intake valve, gives us that it gives us the effective compression stroke, which we can measure in terms of crankshaft degrees of rotation. So finally, let's just go back to the PowerPoint and summarize in our last slide our next step. Based on all those findings, we can clearly present to the customer what is wrong with cylinder 5, that it is cylinder 5 that is our offender. Our next move, what would that be? Obviously, we would now want permission to at least remove the cam cover, and on some of these vehicles, that can be quite an intense process. The picture here, of course, is not from the Volvo, it's just a holding image, if you like. But for example, if this is direct petrol injection, you've got all that to contend with. It may be that some of the VVT control is disturbed as a result of simply taking the camshaft cover off. We know faithfully, based on all our diagnosis here, that that is a worthy process. It is based on conclusive diagnosis that we've captured and stored and saved and can present. And it's probably at this point where the customer will decide, okay, this vehicle, it's really not worth pursuing any further. Or it could be that this is a worthy repair. And of course, if taking the camshaft cover off doesn't reveal anything, then of course, next move, we move on to the cylinder head. My gut feeling on this one, because of that delayed exhaust valve open and close event, and the difference between the effective intake and compression stroke, I would most certainly be looking at camshaft followers, camshaft profile, hydraulic lifters, anything that is controlling valve gear. I think that's a worthy check, along with oil pressure as well. Remember, if this is hydraulic lifters, then oil pressure comes into play too. All right, I hope that helps. And yeah, thank you for watching.